Good morning, everyone. Today I'll be presenting our project on the analysis and power factor correction of a single phase AC circuit. Our main objective was to design, simulate and analyze an RLC series circuit and then perform power factor correction to bring it as close to unity as possible. So in this project, we use multisim for simulation, and our key tasks include is simulating a series RLC circuit, analyzing current, voltage, power and power factor, performing power factor correction to unity and comparing result before and after correction. Here is the circuit we designed. It consists of a 230 volt AC supply at 50 Hz frequency, a resistor of 100 ohm, an inductor of 0.8 Henry and a capacitor of 20 microfarad. All components are connected in series. You can also see the calculation for the peak voltage, which is approximately 325.27 volts derived from the RMS value. This slide shows the simulation output from multisim for voltage and current across the circuit. The waveform here illustrates the phase relationship between voltage and current in an RLC series circuit. As expected, due to the inductive and capacitive reactance, we observe a phase shift which affects the power factor, and something we'll quantify in the next slide. So here are the simulated for power and power factor values. The real power measured was 282.26 watt and the power factor was 0.73, which is lagging due to the inductive nature of the circuit. So this tells us that a significant portion of the power is reactive, not doing useful work. So now let's compare simulation with theory. So in this part I will explain about calculation part, theoretical. For the real power, P is equal to I square multiplied by R. So our current I, which is 1.69 ampere square multiplied by 100 ohm, so give us 285.6 watt. Reactive power Q is equal to I square multiplied by XL minus XC, so 1.69 ampere, same as our current, square multiplied by 251.33, which is our XL, and minus 159.15. So the answer is 263.3 voltage ampere reactive. For the apparent power, S is equal to V multiplied by I, 230 volt multiplied by 1.69 ampere, and the answer is 388.7 voltage ampere. So we also verified the power triangle relationship, confirming that S, the apparent power, is equal to square root P square plus Q square, which is square root real power and square root reactive power. So the answer also gives 388.7 voltage ampere. So it matched our calculation closely. So that's all from me. Go to the next presenter.
Alright, now I will talk about the calculation part for simulation. First, apparent power, S, we need to take the value of V times it with I. So 230 volt times 1.683 ampere, we get the value of 387.09 volt ampere. For real power, P, we take the value of S and times it with the power factor. So 387.09 volt ampere times 0.73047. We have the value of 282.7 watt. For reactive power, which is Q, we take the value of S square minus P square and then we square them. So 387.092 square, 09 square minus 282.7 square, and then we square root them, we get the value of 264.8 volt linear reactors, reactive. It's a bit different with the theoretical data. Okay, now we have the power triangle of the simulation data. So we see the value of Q, which is equal to 264.8 VAR, which is inductive. We also see the value of S, 387.1 volt ammeter, and we have the value of P equal to 8.7 watt. We also have the value of the angle of theta, which is 42.7. And using that theta, we can find the power factor, which is cos angle, and we got the value, so cos 42.7, and we got the value of 0.735, and also it is lagging. Alright, now we will calculate the total impedance C and the power factor. So first we have Z. How to find Z? We need to divide V with I. So V over I, which is 230 over 1.69, we got the value of 136. For power factor, we can use the previous method, which is cos angle and cos using angle, and also we can use R over Z, which is resistance over impedance. So our resistance is 100 ohm, and our the impedance is 136 ohm. We got the value of 0.735. Same with the other one, which is also lagging.
To increase the power factor to 1, we must satisfy the condition of resonance. This occurs when the inductive reactance XL is exactly equal to the capacitive reactance XC. Calculate the inductive reactance to be 251.33 ohms by setting XC to equal this value and rearranging the standard capacitance formula to solve for C new. This gives us the required 12.67 microfarad. Moving on to our simulation results. To achieve a unity power factor, we modified the circuit by changing the capacitor value. Based on our calculations, we replaced the previous capacitor with a specific value of 12.67 microfarad. As you can see in the simulation spreadsheet here, the result is almost instantaneous. The wattmeter now displays a power factor of 0.99985. For all practical engineering posts, this is considered unity. This confirms that our calculated capacitance successful in balance the inductance in the circuit. To summarize the impact of the change, here is a direct comparison between the circuit before and after correction. Initially, with a 20 microfarad capacitor, we had a lagging power factor of 0.735 and a reactive power of roughly 263 VR. However, after correcting the capacitor to 12.67 microfarads, notice that the change: first, the power factor hit 1.0 unity. Second, the total impedance dropped to 100 ohms, which exactly matched the resistor value. Third, and mostly important, the reactive power dropped to 0 bar, meaning no energy is being wasted or circulating between the inductor and capacitors.
This slide shows the circuit after power factor correction. A 12.60 microfarad capacitor is added to cancel the inductive effect of the inductor. After correction, the current is 2.3 ampere and the power factor improved to 0.99, which is almost unity. This means the voltage and current are nearly in phase and the circuit operates more efficiently. After correction, the capacitive reactance equal the inductive reactance at 251.33 ohms. So the total impedance becomes 100 ohm, which is purely resistive. The reactive power is 0 volt ampere reactive. This confirms the reactive power is eliminated and power factor correction is successful. In conclusion, we successfully designed and simulate an RLC series circuit. We analyze the power parameters and the power triangle to understand the circuit behavior. Power factor correction was applied by properly turning and capacitance. Finally, the result we verified both theoretically and through simulation, and they match closely.